Welcome back, everybody. We are now taking a look at section 7.5, day 2, where we are going to be taking a look at how to solve logarithmic equations. And so it's going to be very similar to what we saw with solving exponential equations. So as we get going and we start looking at this process, we don't want to overthink it either as well. Okay, so what we've got to define here first is what is a logarithmic equation. Okay, so let's take a look at that to begin with. So a logarithmic equation is going to be an expression that has a logarithmic where the variable is located. So in other words, you might see something like this. So examples is you might have, let's say, log base 3 of x is equal to 6. Or we can do a little bit more with it, like we could have, let's say, what do we got? Let's say log base 5 of 5x minus log base 5 of 7 is equal to log base 5 of 35. So we've got two different styles here that we're having to deal with, and we'll see how they both work together here. Now, in a very simplistic form, when I have just a logarithm here equal to a value and my variable is kind of tied within that logarithm, we can get to that variable very quickly by switching to its exponential form. So in other words, again, it's all about the base, isn't it? So I'm going to start at the base 3, and I'm going to use that counterclockwise rotation method here, again, that visual that we've been using, and I'm just going to rewrite its exponential form. Take a look. 3 to the power of 6 is equal to x. And 3 to the power of 6 is something that I could then calculate using the calculator, or if I wanted to multiply it out, I certainly could. Okay? But I'm essentially looking at 81 times another 9. Okay? So now how am I doing that? I'm looking at the fact that 3 to the 4th unknown value is 81. 3 squared is 9. I'm essentially doing 81 times 9. So 80 times 9, 720. 1 times 9, 9. We get 729. But the big thing here, everybody, is look at how quickly this happened. All I did when I had just a logarithm set equal to a number with my variable tied to that logarithm here, all I needed to do, change to an exponential form, and I've got it. Now, in this case over here, though, we got a little different situation happening. Now, in our particular problem here, you'll notice that on the left-hand side of my equal sign, I've got an expression going on. Now, in a case such as this, I'm going to need to use my properties of logarithms to condense that down to a single logarithm. So I have to keep in mind, what are the properties that I had? I had a product property, I had a division property or a quotient property, and I had a power property. Okay? So I need to keep all of those in mind as I take a look at my information here. So in this particular case, though, you'll notice we've got a subtraction in between two logarithms that have the same base. Well, that's the logarithm of a quotient. So that would allow me then on this particular problem to write it as a single logarithm, base 5, of 5x divided by 7. Now again, I'm taking the logarithm of that entire piece, but now notice that that's equal to log base 5 of 35. Now notice that everything is the same here on the left side and the right side. If the left side is to be equal to the right side and they're both log base 5, what do you think we could say? Use your logic here. The left-hand side is equal to the right-hand side. They both contain log base 5. What would that tell us about 5x over 7 and 35? Your logic would hopefully tell you that those two parts would be equal. So in other words, when I have two logarithms using the same base, one on the left side, one on the right side, I can set the quantity that you're taking the logarithm of on the left side equal to the quantity you're taking the logarithm of the right side to. So in other words, log base 5 of 5x over 7 equals log base 5 of 35 would imply that 5x over 7 would have to be equal to 35. So I can now go ahead and quickly solve this by doing a multiplication by 7 and a division by 5, otherwise known as the reciprocal, which you all are familiar with. So if I were to do that and multiply by the reciprocal to that 35, I'd be multiplying by 7, dividing by 5, and now I can do some quick multiplication. I don't think I'm going to do 35 times 7 first because that's just going to make a bigger number. I have to divide by 5. I think I'm going to do 35 divided by 5. That's 7. 7 times 7 then is 49. So literally, everybody, you're going to have two different major styles here. One where you've got logarithms only on one side equal to a number, and logarithms on both sides. Okay? So you're seeing the two different ways that we will take a look at these. So as we move ahead, we're going to stick with that. Now, as we go, though, you'll notice that the equations will get a little bit more complex as we work them. But keep in mind that even though it looks more complex, you're still using fundamental concepts that you've already learned about. Okay? So you're still going to be working with what would be considered fundamental steps in solving an algebraic equation. It's a matter of getting our problem there so I can use that. So take a look at example 1, part A. In this case, we've got log base 6 of 2x minus 1 is equal to negative 1. Okay, I want you to pause the video and see if you can get through this problem utilizing what you just saw on the last two quick examples. When you're done, come back, see how you did. In part A, because I've got just a single logarithm here equal to a number on the other side, this is my case where I'm going to switch form and go to an exponential. So notice as I do that, it's all about the base again. I get to say 6 to the negative first power is equal to 2x minus 1. Now, I do need to keep in mind here that now I'm going to have to maybe work with positive and negative exponents, but that's okay. You've seen how that works. 6 to the negative first power, we can eliminate that because we know that the negative first power brings that base down to the denominator as a positive power. Now, if this was a negative 2, then it'd be 6 squared. Well, here we just got a negative 1, so we'll just write it as the 1/6. And notice, you're back to an equation you can quickly solve. Add 1, and then we're going to multiply by 1/2, or divide by 2. My suggestion is going to be to multiply by 1/2. I'll show you why in just a second here. All right, so let's add the 1. So if I add 1, I got to clean this up a little bit. I think I want to get that to be just one fraction. And I'm going to leave it as a mixed, or excuse me, not a mixed number, but an improper fraction. Now, we don't have to make it hard. Denominator is 6, isn't it? Let's just multiply the 1 by 6 over 6. 6 plus 1 would be 7 over 6. Now, many of you I know would look at this and say, okay, now I got to divide by 2. But keep in mind, you're already dealing with a fraction. So a more efficient method that saves a little bit of a mess of generating a fraction over a fraction or embedding one fraction into another is, instead of dividing by 2, think about it in its alternative format. Multiply by 1/2. Now, just because of equality, I've got to do that on the other side as well. But notice right away what this does. It lines up everything you need on the other side right away. So my 2's will reduce on the right-hand side as expected. And now I just got to do 1/2 times 7/6. Well, that's just going to be 7 over 12. And there, everybody, is the answer that I'm hoping you all got to before you actually started going through the key here. Let's take a look at another one. Okay, now this one's got a little bit more going on in it. Okay, so again, before you start the problem, study it a little bit so you've got some idea as to maybe what you can do. Okay, one of those habits we have to get ourselves into is to look at the problem and say, what can I do with it? What is something I can manipulate? What can I do? So here we've got log base 4 of 100, and we are subtracting log base 4 of a quantity x plus 1 equals 1. Now you'll notice in this case, what I can't do is I can't just convert into exponential equation because I've got 2 logarithms. So again, I'm going to ask you to pause the video, try something. What can you do up here and see if it gives you an indicator how to finish the problem? Okay, so go ahead, pause it. When you're done, come back and take a look. In this problem, got a subtraction here of 2 logarithms having the same basis. I can combine them. I can write that as a log base 4 of the division 100 over x plus 1. Now, I've got to be a little bit careful here because now this is telling me that I might have some sort of a restriction here because I can't have a 0 in a denominator. Okay? So we might need to check an answer in the end of this just to make sure it works. Okay? I think I'm going to go ahead and state that restriction just to be safe. Now, I can state that restriction even before I start because when I take a logarithm of a number, I can't take a logarithm of a negative value. So we don't just have to say that x plus 1 is not equal to 0. We have to look at it and say x plus 1 has to be greater than 0. Okay? So we have to keep in mind that because of the restriction on logarithms, you can't take the logarithm of a negative value. We have to look at this piece right here and set it greater than 0. So that means our value of x, whatever it is, has to be greater than -1. If it's not, it won't work for us. Well, let's see what happens. Okay, so again, here's another situation where we've got log base 4, only a single logarithm on the left side equal to a number. Let's convert it. Okay, converting to exponential notation. What do we get to say? 4 to the first power is equal to 100 over x plus 1. Okay, that would be your first major check of understanding. Now your goal, start solving for the x. Well, because of the restriction I stated here that x is going to be greater than -1, I know that I can treat this quantity as a number, which means if I need to get it out of a denominator, I can do so by multiplication. And again, being safe to both sides, using quantity here. Common mistake, people don't write a quantity and then they don't distribute correctly. Now let's clean it up a little bit. Now, this 4 to the first power, I'm hoping everybody's comfortable, is just a 4. Let's distribute. That would say 4x plus 1 is then equal to what? 100. So now, notice to finish off, it's a 2-step linear algebra problem. Let's add or subtract 1. So 4x is equal to 99, and therefore x is equal to 99 over 4 upon the division. Does this fit our restriction? Absolutely it does. There's no doubt that 99 over 4 is definitely going to be bigger than negative 1. So this answer is reasonable to make it work. Okay? So we would be good right there. Okay, let's keep going. All right, so here's the next one. Again, you'll notice that it's very, very common what you're seeing here. The problems aren't all that involved. It's just a matter of using your properties of logarithms to get down to a single logarithm first. Okay, I know I'm out of focus here a little bit. It'll come back in here in a moment. There we are. All right, so look at the third one. So in the third one, we have log base 5 of x to the fourth is equal to 8. Now, this is an interesting situation. I could, at this point in time, convert. And it may not be such a bad thing to do. But I'm thinking, I'm seeing this x to the fourth power here. So I already know that anytime I take a logarithm of something, I have to be dealing with a value that's going to be greater than 0. Okay? So I know that this is going to be positive regardless. Now, I could convert. Let's take a look at it in that method first. Let's say I just convert in this mode. If I convert in this mode, I just got to keep in mind, I'm now doing 5 to the 8th power is equal to x to the 4th power. Now, because x can't be a negative at all here, I can go ahead and solve this using a 4th root. Okay, so it's something that you've already seen. So I can take a 4th root of both sides. And you'll notice that I didn't calculate what 5 to the 8th power is. I'd get this gigantic number that I would end up breaking apart again in order to simplify. If we leave it in its simplified form here, we actually get there a little bit quicker. 4th root of 5 to the 8th, well, would be 5 to the 2nd power. Okay, so recall, 8 divided by 4. Okay, previous material. So what is x? X is 5 squared, or 25. Now, that's not the only way you could actually handle this problem. Okay, so we do have an alternative method to this one as well. It's not all that different, but it'll still get us there. Now, keep in mind, you had a power property that you learned about with logarithms. Where could this 4 also be placed that you've seen previously? Think about that for a moment. We've got log base 5 of x to the 4th power is equal to 8. Recall, because of the power property, I could move that 4 down in front as a multiplier if I so choose. Now, take a look at this. That would say 4 times log base 5 of x is equal to 8. Well, guess what you get to do with the 4? If you do it in this manner, you would have to isolate log base 5 of x, which means a division by 4. Divide by 4. What do we have? We now have log base 5 of x, 8 divided by 4 being 2. Now convert. 5 squared is equal to x. And notice you do end up getting the same thing. So you do have the power property that can come into play on some problems here as well. It's an alternative piece to it. So again, it comes down to, in something like this, really comes down to what you're comfortable with. I'm not going to force you into some sort of a mold if you see it better going this route, where you leave it as a 4th power and then take a 4th root, or power and root in that case, or if you choose to move it down and get rid of it as a division. Both will get you to the same result, and you're still staying mathematically sound. Okay? Now, take a look at this next one. Go ahead and start attempting it here. Okay, get it written down. You've got it written. But try it. Okay, so what do we have? We now have, in this case, log base 12 of x plus log base 12 of x plus 1 is equal to 1. Now, before I start again, though, because I've got this little quantity back here, I got to keep in mind that that quantity has to be positive. So I've got to be looking at x plus 1 and saying if it's positive, it's got to be greater than 0. So therefore, any answer that I get has to be greater than negative 1. Now you'll notice, in this case, I've got to look at it as well. X has to be greater than 0. So when I take a look at these two restrictions here, which one will encompass both? It will be when x is greater than 0. Okay? So when I finish my problem here, I've got to take a look. Does it fit that restriction? Okay, now in this particular case, I want you to go ahead then and try it, pause the video, and then come back. See where you get. Go. In this particular problem, again, we've got two logarithms, both of base 12 on the left side. So we're going to have to combine those. It's an addition, so it will become a logarithm base 12 of a product. X times x plus 1 is equal to 1. Now, I could multiply those together. It would still be a quantity, and I'm going to have to do that at some point in time. But again, that's going to be up to you where you feel comfortable with it. I would look at this and say, okay, I've got it down to base 12 or log base 12 equal to a number. Whatever this expression is, I don't need to deal with yet. I'm going to convert. So in converting, I would get to say 12 to the first power is equal to x times x plus 1. So you'll notice in this particular case, we're going to have a quadratic here. When I multiply through, so I'm going to get 12 is equal to x squared plus x. I got to solve this like a quadratic, which means what? Get a 0 on one side of the equal sign. So I'm going to bring that 12 across by subtraction. So x squared plus x minus 12. So now, in most of these cases, you're not going to be dealing with, for the most part, having to use a quadratic formula, although you could. Again, I wouldn't go to completing the square because the quadratic formula essentially takes care of that for us. So you're really down to two options. Factor it or use a quadratic formula. I think in this case, I'm going to factor it. Now again, because I've got the 1 in front of that x squared, we've already learned that I can take that right to binomials if it factors on its own. Well, let's see if it does. Two numbers that multiply to negative 12 that add to 1. Now keep in mind, one's got to be positive, one number's got to be negative, and if they're adding to a positive, the bigger of those two numbers has to be the positive. So if you're thinking 4 and 3 to make the 12, you're correct, and the 4 would have to be the positive. So we could argue x plus 4 and x minus 3. Now you should know exactly where to take it from here. We're going to go ahead and separate and solve. So you'll notice that in this particular instance, you have two potential answers again. So x equals negative 4 and x equals 3. Is it possible both work? Of course it is. But how do I know? I got to go back and look at my restrictions. Let's take a look at those restrictions again. Okay, from the first quantity, x had to be greater than negative 1. In the other quantity, x had to be greater than 0. Well, x is greater than 0 has to work then for all of them. Well, look at your two values. We should be able to argue here that x being negative 4 would be the extraneous solution. We cannot use it. Why? Because if I come up and try to take log base 12 of negative 4, I would get an error on my calculator. It doesn't fit the domain. Again, keep in mind that value has to be greater than 0. Here, I've got to be greater than -1. We'll put a -4 in here. -4 plus 1 is -3. Again, you're taking the logarithm of a negative. Not allowed. The 3 works, though. Log base 12 of 3. You could calculate that. Throw the 3 in here. Log base 12 of 4. You could calculate that. So again, you will run into situations where you will need to deal with quadratics, factoring, completing the square if you choose. Again, I'm not recommending that. Or you have the quadratic formula. Okay, so you can't let that stuff go that we've previously seen. It still is showing up. Okay, so with that in mind, you're not going to be dealing with too many application problems with these. This is primarily going to be an assignment that is mechanical. Okay, so you're not going to have to worry about trying to figure out, okay, what variable is going where in a logarithmic equation. Okay, I know I'm a little blurry here again. It'll come in. Oh, at least my hands. There we go. Okay, so from there, everybody, I'm going to let you get going on section 7.5, day 2. You can expect that there will be a lesson quiz after this as well. So again, we'll take a look at everything in here. Go ahead to the live feed when we're set to do that. We'll see you there for some questions. From there, have a great day. Stay safe, everybody. Bye-bye.